Hello everyone, this is the ICPC 2024 World Finals Problem G, Kindergarten. You're given a directed graph where every node has one outgoing red edge and one outgoing blue edge, and the blue edges form a cycle and several rooted trees hanging out from it, and you need to find the permutation of vertices such that for each vertex pi, if its blue edge goes to vertex pj and its red edge goes to vertex pk, then one of the following is true. Either vertex pj is to the left of vertex pi, or if vertex pj is to the right of pi, then pk is between those two. This is a very tricky problem, and this is only going to be a short solution summary, but hopefully it's still going to be informative. So first of all, let's consider what we have in this problem. Let's look at the left picture. Like I said, we have a cycle of blue vertices, a cycle of blue edges, and then some trees hanging out from the vertices of this cycle. For example, C and A are two vertices of this cycle, and we have some more. Now, we have an edge from C to A, which is the only edge which doesn't belong to the tree. But let's say that there is no such edge, and we just root everything at vertex C. In this case, the actual permutation that we need to find is just the topological ordering, top to bottom. Like we just traverse this tree using any algorithm from top to bottom and print the permutation, and then for each vertex, its blue edge is going to go to the left in the ordering, so it's going to be fine. But the only issue is vertex C, because we have an edge from C to A, it might be that our condition for vertex C and only for vertex C is going to be not satisfied. And we need to look where the edge from vertex C goes, I mean the red edge. And there are two main cases. For example, if the edge from C goes to the subtree of A, then that's the hard case. We're going to describe that later. But if it goes somewhere outside of subtree of A, which is the right edge on this picture, then our permutation can just be the ordering of everything besides the subtree of A from top to bottom, and then the subtree of A. And in this case, the condition will be satisfied for all vertices as before, but also for vertex C, because the red edge from C is going to go to vertex which is going to be between C and A, so we win. But the interesting case is on the left as described. So in general for this problem, we're also going to be using this condition a lot. So let's look at the following sub-problem. We have a tree of blue edges once again, and we have two vertices x and y on this picture, and we want to figure out whether there is a permutation where all the conditions are satisfied and vertex x goes before vertex y. So once again, if we want that condition to be satisfied, x to go before y, it means that wherever the red edge from x goes, that vertex has to be between x and y in the ordering. So there are actually three main cases here. First case is when the edge goes to the subtree of x. The second case is when the edge goes to the subtree of y but not x. And the third case is if the edge just goes somewhere outside of the subtree of y. And it turns out that in cases 1 and 3, it's easy to find the permutation. It's going to be similar to what we described before, but the interesting case, again, the hard case, is when the edge goes to the subtree of y but not x. This is number 2 on the picture, and we will call this situation that the edge from x goes to its sibling descendant, that is the descendant of x's sibling, literally. We are going to mark those edges with SD. So now let's consider what happens in general let's go back to the original problem. We have vertex A of the cycle, and we want to find a permutation where, let's say vertex A is the last vertex in the ordering among the vertices of the cycle. And C, once again, is the previous vertex in the cycle. And let's consider just the subtree of A plus the vertex C. And we can see that nothing for this case outside of this subtree matters for us. And we are going to introduce a new concept, which is we are going to mark vertices with green in the following case. A vertex will be marked with green if in any valid permutation, if we take this vertex and all of its parents up to A, then they have to go in this permutation exactly in order from top to bottom. So A, and then the next vertex, and the next vertex, and so on. And as a reminder, we also want basically to find the permutation where C goes before A. So that's relevant to the previous case that we just drew, where I guess C corresponds to X and A corresponds to Y. So we want to find whether there's a permutation which satisfies the following conditions. So now we have this marked vertices definition. A is marked, and we want to extend this set. We are going to extend the set of vertices which are marked using two different rules. And the first rule is going to look like this. Let's say we have vertex V, and let's say its blue parent is already marked, but also the red edge from vertex V goes to some sibling descendant of itself, and then that vertex is also marked. In this case, we can see that vertex V also has to be marked. So what does it all mean? Basically, it means that, again, we want to check whether we can pull vertex V above its parent in the permutation. If we pull vertex V above its parent, it means that its parent is going to be after V in the permutation, so we need the red edge from V to go somewhere between V and its parent in the permutation. So, but in the case when that vertex is marked, this vertex to which the edge from V goes, it means that it has to go after the parent of V in the permutation, which is a contradiction. So it means that we cannot pull V above its parent, which means that V can be marked now. And the second case is on the picture on the right, and now it's a bit more complicated. Let's say we have a cycle of edges, of red edges. So we have vertex V, and the edge from V goes to some sibling descendant of V, and then the edge from that vertex also goes to a sibling descendant, and so on. And all the edges in the cycle, in fact, except for the last one, which goes back to V, go to sibling descendants. And let's also say that all parents of vertices of this cycle are already marked with green. In this case, we claim that vertex V can now also be marked with green. Why is that so? So the proof is somewhat similar. We want to pull vertex V before its parent in the permutation, and then it means the next vertex in the cycle also has to be pulled, and then the next one has to be pulled, and so on, and this one has to be pulled. But then the last one, for the last vertex in the cycle, the condition is not going to be satisfied, and we are going to get a contradiction again. So we are going to apply these rules while we can, and mark in the vertices. And why are we doing that at all? So basically, if we find that vertex C is marked, we will find that it's impossible to put C before A, so it means that this choice of A and C doesn't work. But if it's not marked in the end, then it turns out we can actually construct a permutation. We are not going to go into the details of how we do this, but we do this by tracing some path from vertex C by red and blue edges until it loops onto itself or goes somewhere outside of the subtree. And there is some casework involved with this, but we can show that we can always find a valid permutation in this case. So once again, this problem is pretty tricky, and it's very hard to get all the details right, but I hope with this explanation I gave at least some idea about this problem. Again, a very complicated problem. Hope you enjoyed it. Thank you for watching, and goodbye.